When we think about AI, we usually picture it dealing with cold, hard facts, right? But the real world, it's messy, it's uncertain, it's full of maybes. So how does an AI figure things out when it doesn't know something for sure? Well, today, we're going to dive into the really powerful probabilistic models that let AI move beyond simple, rigid logic and into this fascinating world of intelligent guesswork. It's something that starts to look a whole lot like human intuition.
Think about a robot exploring a brand new place. Its sensors are feeding it data, sure, but it's not a perfect picture. The robot might not know its exact location, but it can use probabilities to make a really good guess. And this is a classic AI problem. How do you operate with incomplete information? It's way more common than you might think.
And look, it's not just about robots. Whether it's predicting tomorrow's weather based on what's happening today, or an AI understanding what you're saying despite all the background noise, the ability to handle probability is absolutely crucial. Instead of knowing something with 100% certainty, AI often has to work with the likelihood that one thing is true over another. And to pull this off, it needs some pretty special tools in its toolkit.
Okay, so the first tool we're going to look at is for mapping out how different things influence each other. It's called a Bayesian network, and it's just perfect for modeling a complex web of cause and effect.
All right, so what is a Bayesian network, really? The easiest way to think about it is like a diagram. Each circle, or what we call a node, represents a variable, something like, is it raining, or is the train delayed? Then you have arrows connecting these nodes, and those arrows show you which variables directly influence others. So it's basically a visual map of dependencies, where the parent nodes are the causes and the child nodes are the effects.
Let's bring this down to earth with a simple, everyday scenario. Just imagine, you've got this super important appointment across town, and you have to take the train to get there. Whether you make it or not, well, that depends on a few different things.
And right there, you can see how the structure starts to build out. Making your appointment, that's directly dependent on whether the train is on time. Simple enough. But the train's arrival, well, that's influenced by two other potential causes. Is there track maintenance happening? And is it raining? See how we're building this web? We're connecting all the variables that affect our final outcome.
Okay, but here's where the magic really happens. Each of those connections, each arrow, isn't just a line. It has numbers attached to it. These are what we call conditional probabilities. The network actually stores the likelihood of something happening given its causes. So look at this table. If there's no rain and no maintenance, there's only a tiny 10% chance the train is delayed. But if there's heavy rain and track maintenance, wow, the probability of a delay shoots all the way up to 80%. This is what lets an AI calculate the chances of you missing your appointment just by knowing it's a stormy day. Pretty cool, right?
So Bayesian networks are fantastic for all those interconnected causes. But what about predicting things that happen in a sequence, one after another? For that, we've got to turn to a whole other kind of tool, Markov models.
So the whole idea behind Markov models is actually really simple. It's called the Markov assumption. And what it says is basically that to predict the future, you don't need to know the entire history of everything that's ever happened. All you really need to know is what's happening right now. It's almost like the model has a very short-term memory.
So what does that actually mean? Well, it means that whether you're predicting the next word in a sentence or the next move in a game, the model just assumes that the most recent information is the most important. Everything that happened before that, for the purpose of the next prediction, it just doesn't matter.
The absolute perfect way to think about this is the weather. Sure, the weather last week might have some small influence, but your best clue for predicting if tomorrow will be sunny is knowing that, well, today is sunny. The current state, today's weather, is the most powerful predictor of the next state. And this sequence of states is what we call a Markov chain.
All right, but what if we take this a step further? What if the thing we actually care about is hidden? What if we can't see it directly? This is where an even more powerful version comes into play, the Hidden Markov Model, or HMM for short.
Let's really break down the difference here. In a simple Markov chain, we can see the state directly. We know it's sunny outside. Easy. But in a hidden Markov model, the true state is invisible to us. We don't actually know the weather. All we can do is observe things related to it, like seeing a bunch of people carrying umbrellas. The AI's job is to take those observations and infer the most likely hidden state, in this case that it's probably raining.
And this isn't just some abstract idea, right? This is the engine behind some absolutely incredible tech.
Your phone uses hidden Markov models for speech recognition. It's inferring your words, which are the hidden state, from the audio waves it observes. And that navigating robot we talked about at the beginning? It's inferring its hidden location from all its sensor data. HMMs are a true cornerstone of modern AI.
Okay, so let's zoom out for a second. When you put all this together, a really clear picture starts to emerge. The ability to reason with uncertainty, it's not just a neat feature of AI, it's what lets it act intelligently.
So we've seen how Bayesian networks help AI understand these complex webs of cause and effect. And we've seen how Markov models let it predict the next step in a sequence, even when the most important info is hidden. And look, these aren't just clever math tricks. They are the actual frameworks that allow machines to make sense of our messy, probabilistic world.
When it comes down to it, this jump from a world of absolute black and white certainty to one of probability, that's what really elevates AI. It transforms a machine that can only follow rigid rules into a system that can infer, predict, and make sophisticated judgments based on evidence. A lot like we do.
This power to actually quantify and think about maybe, it's one of the biggest leaps forward for artificial intelligence. It's what allows AI to start tackling some of the most complex, uncertain challenges we face, which leaves us with a pretty fascinating question to think about. Now that AI can master maybe, what uncertain future is it going to predict next?